to some analysis that we are developing together with Francesco very recently on so higher order, fractional order, and constitutive relationship. At the same time, I would like to present to you a connection with this kind of research of some previous results that we obtained in order to couple and to put inside the continuum systems that contains inner resonances, exactly in the same manner that the previous speaker was introducing. So, this is just a layout of the presentation. As a first point, we would like to spend some words on some classical interaction rules. And the second point, we would like to address our attention essentially on three elements. So the first point is the distinction between short and long-range interaction. So if you have, for example, a lattice, or you have a structure that is composed by many particles, so we would like to study the differences that can be introduced, just modulating the range of interactions. So if you are interacting, this particle is just interacting with the closest particle, or these particles are interacting with very far particle in lattice. So we have completely different kind of constitutive relationships. So the second point is the distinction between static versus dynamic interactions. It means that generally, looking at the usual way of building a theory of elastic material, we just are considering elastic interaction between particles. But this is, of course, not the only way that they can interact. In fact, they can interact by electrical forces or electromagnetic forces that indeed have also a long range of interaction. And indeed, they can be connected by complicated systems, mechanical systems, just including unmonitored degrees of freedom. So you can have hidden masses inside. Then you want to take into account the third point that we don't want to discuss today is the distinction that is very fundamental between the atomic potential in the interaction between particles and the triatomic potential or polyatomic potential. It means that the modality of energy storage into continuum can be defined by different ways in which the energy is stored into the system. So we, in point 3, will consider exactly the point of short versus long range interaction. And so we have a link, especially with the mapping state of this morning. And in section 4, we have a very systematic comparison between static and dynamic interaction and with the problem of unmonitoring. So we want to describe models in which we describe only a part of the system, especially when you have a lot of degrees of freedom. This is especially true when you are designing very complicated aerospace structures or automotive components. And then you want just to monitor a limited part of it, but you want to take into your equation the effect of the coupling with the part of the system that you are not directly modeling. And this is, of course, for this reason, we have a very close link to, again, to the closed talk and to the mapping stuff of this model. So we want to just explain the subject and to illustrate the subject for the linear chain, because conceptually there is not a very big difference considering more complicated systems. So we are considering just a linear chain. So a linear chain of particles in which each particle is a concentrated mass, and at the beginning we suppose that they are elastically connected. So what are the classical or usual interaction hypotheses that are introduced? So the first one is that we have short-range interactions. So we interact only with the two closest particles in this case. So one particle is just interacting elastically with the closest particle. And the second hypothesis is that the energy storage if L1, Fn are the coordinates of these particles, so the energy storage can be expressed through a potential function type that depends only on pairs of particles. This is indeed quite special hypothesis that is introduced and has some implication in the equation of motion of the system. As a third point is generally in elasticity, we suppose that we have a linear static interaction, essentially based on attractive spring-like forces that depend only on particle positions. This is indeed natural for very, even for usual system, for example, in M&MoCS. I'd like to show you a very appealing example in which you have that the interaction forces are of electromagnetic type, in which spring-type forces are just one of the components of the interaction. So, as an additional point, generally we think that about a characteristic of the particle in the system. And the mass generally is the only particle property that we introduce. But for example, if you have an electrical system, you have, for example, that the charge at that point is another characteristic of the system, especially if the masses cannot share charge. If they can share in the charge, you have an additional Lagrange variable to describe the system. Another point, the particle displacements are indeed the monetary quantities. It means that generally, when you are building this model, the particle displacements are selected to play the role of unknowns. But this is not the only possible choice. For example, we can decide to monitor linear combinations of particle positions, for example. A sort of moving average. It is a different way to describe the system. And so this can change, of course, the custody relationship. And then another possibility is that you want to exclude some part of the system by the direct monitoring. So you don't want to write explicitly all the equation of motions for each part of the system. You want to just represent one part of the system. I would like to say that this is the general way in which we approach the mechanical problem. Because indeed, when you are describing any kind of system, you are just modeling a finite part of the universe. But of course, if you want to model any kind of interaction, there is no limits to this kind of description. So, in some way, when you introduce some force into the system, it's just the sign that you are limiting your system to a finite part, a finite portion of the universe. That is indeed something that you are compelled to do in order to avoid to model the entire universe. So, look at the problem of short-range interaction. So we would like to remove these limiting hypotheses. So we can introduce long-range interaction. So the particle forces range from the closest particle to far particles along the chain. So we can introduce the short-range one-step interaction or two-step interactions, like in this drawing, or again, a force range that is covering 3 steps. Or in general, as we will introduce later, we can have that each particle of the system has the possibility to interact with the remaining part, all the remaining parts of the system. So about the diatomic potential interaction, this is just a very special choice. For example, in atomic lattices, the interaction force between 2 atoms or among atoms does not depend only on the distance between atoms, but for the hybridization of the orbitals, it depends also on the angles that you have considering triplets of atoms. And so the general form of the energy storage contains this term, but contains also another function that takes into account more complex type of interaction in which you have the dependence on the triplets or in general or higher order potential interaction. So the third point was linear static interaction, so spring static forces that depends on the particle position, but we know that in general, and this is the case that was also considered in the previous talk, suppose that you have particles along the chain, but they interact not only by the spring that is interposed among the two, but you introduce an additional system. So the particles are just connected through a system S. And in general, these systems can vary along the chain, so have different properties along the chain. And this is a totally different problem, because we have in general into the system as additional degrees of freedom. These additional degrees of freedom can be of mechanical nature, if you are just including masses there, or in some cases, you can have also a system that is of mechanical, electromechanical, or electronic nature inside. Another point that is also related, as we said, is that the mass is the only particle property descriptor. This is not eventually true if the particle can be characterized by two or more parameters, like, for example, electrical charges, magnetic moments, or chemical quantities, and so on. We would like to show in the following the case in which you are characterizing each particle by two parameters, the mass and the charge. So you have a completely different way of behaving of the system. Suppose, additionally, that you permit the charges that are on the particle to move along the chain. This is a very nice example that I would like just to show you. For example, even without any contact, it is very usual and very popular in a non-mechanical system that you can have an electron flow along a chain of oscillator just because of the tunneling, quantum tunneling property at that scale. So you have the charge on which resonator, which particle can change during the motion, and then you can introduce, for example, the charge and the displacement as the Lagrangian variables. But of course, when you have charges on the particles, of course the constitutive relationship is completely different. And so the motion of the system is completely different. This is an example that we are studying that is related to the realization of a nanomechanical transistor. So the idea originally is that you have a set of resonators, as you can see here. It's a set of pins, nanopins. They are elastically coupled. So you have pins that are covered by elastic torsion springs. Okay, it's very simple system. And you have another beam, another pillar, that is the so-called driving element of the transistor. Then you have here, and here, you have electrons. And you have that the caps of these beams are conductive. Then you apply on these two electrodes a voltage. And then you have an electrostatic interaction between the beam and the electrons. So it is very, very nice that in this part of the system can travel an electron flow. But the electron flow is coupled to the mechanical waves that are induced in this process. So it is a very nice problem in which you have a coupling actually between the electron flow and mechanical wave. It is very nice that this kind of system can exactly work like the components of electronic circuit, in the sense that if you apply a voltage to the drive resonator, you can control the current that is transmitted along with the collector emitter line. So it is a sort of revenge of our mechanical people against electronic. So this probably. We hope this is the future of many problems in mechanics.
Not exactly. It could be a good valve.
This is not
It could be a very good valve.
Yeah, it could be. But the main point is that it contains a lot of dynamics, a lot of mechanics. And indeed, the people that is involved in this kind of research generally do not come from our field. I say our field, I am in the field of mechanics and aerospace, but I think that the same is true for you. So, generally we have people from physics that in some cases can even reinvent the chemoscientific material. So it's something that we have to consider. So, I would like to talk about the short-range interaction. So, very simple physical consideration. So this is the equation of the motion for the Donald system. You have just a single particle that is interacting with the two closest. These are, I put here one in order to indicate this is the one-step interaction. So you have that the interaction range is just delta, and delta is the distance between the two particles. Then I would like to extend the range of interaction, passing to step 1 to step 2. So I have two contributions. The first contribution is the short range, the second contribution is the long range. Delta is the distance. Then you can define these two simple parameters. One is mu, and the second is beta. Beta is a positive parameter and is a finite value. So when you have that delta becomes small, you have that delta tends to 0, beta is positive and finite. This is the finite counterpart of that equation. Meaning that if you put this equation on this line, you can get in the limit this equation that is formally similar to the motion. We would like to explore what is the possibility of realizing a system like that, because of course it depends on the interaction forces that you are considering here. Note that because beta for stability reason must be positive, you have that a short range interaction is a sort of it's characterized by positive interaction because it is meaning that it has simple elastic force. So it can be realized by simple elastic force. But this is not true for the long range interaction. That with this position must be a negative interaction constant, and it means that it cannot be realized by traditional mechanical interaction forces. The nice thing is that pull-up-like interaction can mimic the negative constant effect. For example, if you consider a chain of electromagnetic dipoles and springs, you can realize this effect. For example, if you have a chain in which you have equal masses, equal springs, and then you have alternate signs in the charge. So you have a double effect that you have repulsive forces in the long range, say 2 steps, and at the same time you have the chance of long range interaction because there's a Coulomb force is of course decaying with the square of the distance, but of course you have an effect even at a certain given distance. And so not only with the closest part. And then you have a relationship, simply stress-strain relationship that can be described by this equation in which the first advent is due to elastic interaction, but the second advent is due to the Coulomb force interaction. I would like now to have a connection with the markets of this point. Suppose that now we want to extend this model, considering all the possible interactions along the chain. So each particle along the chain can interact with all the remaining set along the chain. So the equation for a single particle is simple, expressed by this equation, in which the first summation just expresses the forces with the preceding preceding set of particles, like the second simulation, is the interaction of the considered particle with the following set of particles. Then we just consider that delta is small. Then we approach the summation by integrals, and we introduce these two kernel functions, k plus and k minus, that are kernels that actually describe the way the interaction forces decay with the distance. Now, it is very nice that these integrals have the form of something that is very close to a fractional domain. Suppose, in fact, that we decide to model this interaction kernel in a fashion like that, in which you have something that is in a sort of inverse proportion with the distance. And suppose that we select the Q parameter that is in the range 0, 1. So suppose, for example, that you want that the interaction forces goes like 1 over the square of x minus psi, meaning that Q is equal to 0.5. If you assume this, and then you look at the form of these integrals, and you introduce the Riemann-Wigel definition for fractional derivative, what is very nice is that this is the equation of motion for the system. So actually, the interaction forces are directly described in terms of fractional derivatives. As Martin mentioned this morning, in this case you have fractional derivative of a constant. This is not a constant indeed, but is a function of x. So this is very nice overview, because you have in this case just shading speedily. The way the interaction forces decay on the chain, you can get a stress-strain relationship that is described easily by considering this equation.
So you also are not happy with n of the gradient because you want n not being integer.
It comes out that sometimes you have not an integer relationship. Now I'd like to talk indeed about something that has been considered by Claude in the previous talk. So suppose that our particles are connected by complex dynamical systems, S, so that contains degrees of freedom. For example, in this fashion. This is not the only way in which we can consider the internal part of the system, but I would like to tell you that this is much more general than one can initially think, because we can reduce by the use of model analysis any kind of interiors for our system in a fashion. So suppose that, just for sake of simplicity, that we have capital mass for the big masses along the chain, and we assume that the masses that are contained into the system are indeed very small with respect to the n capital. And we assume also that the number of the small masses is much larger with respect to the number of the capital masses. So we have a very high number of small particles contained into the interacting system, and the mass of the system is very light with respect to the mass of the chain. With this hypothesis, we have results that are a little bit different with respect to the result that you presented today, just because of this different hypothesis. So, in this case, our added mass effect is very small. Is in the limit that m is very small. Actually, in our experiments, it is 3%, 4% of the total mass. The added mass effect is negligible. But the nice thing is that the effect of this hidden cluster of degrees of freedom is to generate damping in the system. Even if you have not any kind of dissipation in the system, it's a sort of energy sink, energy storage. So the energy is So our goal is to describe the motion of the chain masses. So we want to take, of course, into account the dynamic happening with the small length. But we don't want to explicit the equation of motion of the small mass. And this is a process that we can call M-monitoring. So we don't want to describe anything. I would like to tell you that this is an approach that is common, for example, in physics. So if I have any kind of description of any kind of system, typically this system is interacting with the environment. For example, in Brownian motion. Brownian motion is just the first example that historically use this kind of approach. So I want just to monitor a single particle, and then I want to monitor the particle that are part of the environment, that are interacting with the particle that I'm following. And then it is not foreign that you have a Rangevin equation description for this kind of system that we will introduce. Now, our hypothesis is that capital M is much larger than small m. The second hypothesis is the number of the small mass is larger with respect to the number of the capital m's. And the third point is that we have a special distribution of stiffness inside the system. Special distribution means that without this special distribution, we have not the ability to produce them at random. But we demonstrate that the kind of damping, the kind of distribution that we need for our system is Gaussian-like, meaning that you need that actually that the distribution of the stiffness inside the unitary part of the system. So this stiffness have a random distribution, and this random distribution is concentrated around an average, and then you have a sort of dispersion around this average, and the shape of the probability density function is more or less similar to a Gaussian distribution. Under this hypothesis, then the dynamic coupling can be reduced to an equivalent damping effect, and this is in the absence of any dissipation of the coupling. So the effect of damping that you introduce is not trivial. Can be also treated. So if you select properly the stiffness along the system, you can have even the trivial case of viscous damping. But if you select properly the stiffness in the equal subsystem S, you can obtain fractional derivatives damping. And I don't know if I have time. Okay, just I would like to give you further insights into this problem. The first moment, so I discovered that after 5 years working on the problem. So the very first model that introduced a master element coupled to a cluster of resonators was considered in 1963 by Feynman and Vernon, in a very beautiful but very difficult work. Probably this is the reason why it is not so largely considered in this work. The second paper, the paper that was published by Carcaterra and Leggett, these are Carcaterra and Leggett, two famous physicists, in 1983 is indeed more known, more widespread. It doesn't contain really a very big novelty with respect to the paper published in 1963, but it's much more easy to read. Probably the reason why this is more famous about the first, really the second first. So, if you look at the way in which you can, this is the way that I'm showing to you, is exactly the same line in which in 1914, Langevin introduced the concept of the description of dissipation in Brownian motion. So this is the philosophy that is behind this. So you can describe the motion for the big mass, and this is just this term, plus the interaction with the small masses that you have along the top of the big mass. And then you have a set of n equations, each for the small mass that are attached to the mass. Now, the goal is that I don't want to describe the system by using these variables, but I want to describe the system just using x, n. So this is the challenge. So, are we able to describe in a single equation the property of the big mass? So, neglecting at all the presence of xi, the formal presence, because we want to take into account the physical effect. So, we want to describe the interaction forces just in terms of xi. So the analysis is not conceptually very difficult. So you can write in a matrix form this equation, and you can separate very easily. It's a linear problem. You can separate the equation of motion for the single mass that you want to consider, and then you have a system of equations that describe the remaining part of the system. Now, what happens is that in the first equation you have the contribution from the degrees of freedom that you don't want to cancel implicitly in your motion. Of course, the reverse is true. You have the contribution in this set of equation of because this is exactly the coupling in the two systems. Now, it's very easy because what we want to do, I want to consider this term as a force for this system. Then I can get a solution for this, and then can I substitute this solution here, just express it in terms of x. This is just a substitution. At the end is very conceptually is very easy.
Forgetting about initial data.
Forgetting about initial data, if you cancel the problem of initial data, you are introducing the so-called fluctuation terms. So this is the dissipative part in Brownian. So you have the double fluctuation and dissipation. This is the reason why there is a famous theory that is fluctuation and dissipation theory. So we are neglecting the fluctuation part. Then you can solve the technical, it's just 3 technical steps. So the idea is that you can take the Laplace transform of the Wood-Settle equation, then you obtain an algebraic set of equation, and then you can substitute everything into the first equation that represents exactly the motion of the mass. So that's very tricky. The result is indeed very intriguing. So what we obtain is an equation of motion like that, in which, as was the initial idea, you get the inertia term, the proper stiffness of the mass, and then you have here, in this convolution integral, you contain anything about the interaction with the remaining part of the binomial system. Now, the fact that this is a sort of, this is a convolution integral, suggests that the behavior of this term can have very special properties. So suppose we develop this kind of equation for the system that is simplified with respect to the general case. Following the same procedure that I was showing to you, trust me that this is the result. It's very simple. So you obtain that this is the equation for the master, and this is the interaction term that we can call environment operator, because it takes into account the interaction with the remaining part that we don't want to monitor of the system. The kernel of this integral contains in it m, that is the mass that is coupled to the master. Omega I are the eigenfrequencies of the coupled systems, and then you have something like that. This is nothing else than this is something that just has inside the impulse response of the oscillator to attach it to the system. Suppose now, just to show you how you can generate damping by this process. Suppose now that this is a summation, then you have a limited bandwidth in which you have natural frequencies of your system, and then you increase the number of particles leaving the mass ratio between the total mass of the mass and the total mass of the cluster, vibrating cluster, and output. So this summation is expressed by this integral, and the property of the kernel that you have there actually depend only on this special function that we call the mass spectral density. It is the amount of mass that is vibrating attached to the system in a given frequency band. That's all. This is the driving parameter. So just the amount of mass of the attached system that is located for frequency band. This is a function that can have a shape that you can just decide at the design stage. And I would like to show you that easily. If you have that, for example, you select the spectral mass that is in inverse proportion with the square of the frequency, you have that this integral easily leads to a viscous number, even if you didn't introduce any kind of dissipation. It's just that the energy goes naturally from the master to the cluster of oscillator. If you modify suitably the spectral mass, meaning the design of the cluster of system in terms of springs and masses, what you can get is any kind of dissipation effect you want. And as a special case, and reminding that this is the fractional derivative definition by Neuville-Green, you can get also the case of fractional derivative constitutive relationship. But I would like to show you if it works, some physical demonstration of this analysis. So this is a very simple system. So you have the principal mass, the master mass is a T-beam. And then we attach to this T-beam a set of filaments, iron-made filaments. The total mass of these iron-made filaments is 3% of the total mass of the T-beam. And we selected for the natural frequency of these beams a distribution that indeed controls the diagram that we want to determine. So in the blue figure, you have the response of the primary in the absence of the vibrating filaments. And in the second one, you have indeed the response of the beam, T-beam, when you apply the small resonance. What is apparent is that a very quick transfer of energy from the primary is transferred to the cluster.
So you don't have that beautiful movie?
Yes. Maybe that's I was, if you know that, you for sure. So, for example, in this case, the equation of motion is written in this form. These are two classical terms, but this is indeed the new terms that takes into account the effect of the hidden cluster of the zone. And it's quite intriguing that you can shape the way you like this term in order to obtain special effect. If we remove some of the hypotheses, this term, because of course this term contains also added mass effect, additional stiffness, and additional number. In the case of the hypothesis that we introduced, the main effect is in damping. But of course, if we neglect or we remove the hypothesis, this can generate also a very complicated added mass effect. Just looking to this procedure, even in engineering, it's not really uncommon that this process of unmetering is considered. For example, if you think to aeroelastic products, we should have the coupling between an elastic structure and the fluid flow. But actually, when you develop the equations for the flat, you don't model actually the flow. You have just the effect of the flow on the elastic response of the system that is just taken into account by special currents. The Theodorson current is exactly what you introduce in elasticity in order to take into account the unmonitored part of the system. For example, look at that set of resonators. I'd like to show you. Okay, this is the frequency on the x-axis, and on the y-axis there is the equivalent damping that was determined on the basis of the kernel analysis, so the previous theory that I showed. Then I tried to make an experiment. So suppose that I don't know what kind of guy is that central resonator. I just use an identification process. So I write down the equation of motion, and I say, this is the equation of the system that I am considering. It's just a linear oscillator. I made an experiment. I know this term. I know x dot, x2 dot. I know the mass. In this case, stiffness is not present. And I can identify C. So I can identify its experimental C. And this is the C that is identified. And as you can see, it appears that it is similar in shape to the correct prediction. So you want to have a peak in this case around 440 Hertz. And in fact, you obtain that this is the damping. I would like to consider this, so the conclusion of part of this presentation is something that generally lead to a fight with some colleagues in engineering. So the conclusion is that damping is not a measure of dissipation of the system. Not at all. So damping is something that is completely different with respect to dissipation. So we can have even dissipation-free system that indeed exhibit damping. So there is not an equivalence between the two concepts. So it, in some sense, it makes very uncomfortable. People that is, for example, making experiments on determining the damping of a material. It's not a property of the material. It's a topological property because it depends on the shape, it depends on the space distribution of the mass. So it is something that is a subtle concept, but that indeed seems to be. Now I'd like to show you now a movie that is nicely illustrated.
Usually engineers are not studying the physics of finding.
Well,
Lecture notes that this is written.
Hold on. As you see here, this is the master. It's a simple oscillator. This is a gas bearing just to diminish the intrinsic damping of the system. So this is just to show you that the system is very dissipation-free. It is just a 1 degree of freedom system. Now, in the second experiment, we attached a lot of pendulum. The frequency distribution which is conformal to the theory. And then we want to see if the energy goes there and there remains. And then you can see this. And then you can see that the master is damped and the energy is flowing towards the center resonators. And this is something that illustrates physically the concept that is behind, in this case, the Langevin equation. And,
Okay, now I know the answer, but tell why Poincaré theorem is not contradicted.
Well, because the observation times are completely different. The scale of observation times. So if you wait enough patience,
How many did you calculate in Carcaterra time for that?
one is unbelievably longer than
The movie.
Okay, that's all.
Thank you very much for this interesting models and experiments. So, some questions, Martin?
We have dashboards, yes, and dashboards in linear,
Dashboard where?
when you have dashboards, when you place dashboards in this scholastic model,
Yeah.
you assume that it's linear or
You assume that they are the corresponding dashboards to the frequency distribution that you have inside the cluster of reasoning. So there is a correspondence between the two.
I didn't get the analogy to the Caldera Leggett model.
The analogy,
They have like huge number of quantum resonators with huge microscopic also.
yeah, the main problem that was, so what is the reason why Feynman and Bernoulli has Caldera Leggett introduced that model?
Yeah.
The point was, they had the Schrödinger equation for
Okay.
quantum mechanics. Now the problem is that the Schrödinger equation is determined on the basis of the Moberly principle,
Yes.
Hamilton principle.
Right.
Moberly principle does not include any kind of dissipation. It is conceptually grounded to establish quantum mechanics in the presence of dissipation, because Moberly analysis does not introduce any kind of, because it is not included into the. So say that at atomic level you have not dissipation, you have redistribution of the energy. Now, they had the problem to extend the result in the case of presence of some dissipation mechanism. And then they developed this model that indeed can introduce some damping, but without dissipation. That was the reason. This is the analogy. What they didn't do is, of course, to shape properly the kernel.
Yes.
And the reason is that they know that in nature the kernel has a particular shape. So the way that it came with the frequency of the kernel is sort of natural property of the matter. But in engineering, we have the freedom to select the shape in the best way.
Yeah. In measuring systems.
Yes.
I see.
Okay, Patricia?
If you consider the multi-body interactions, three-body interactions, or alternatively interaction between particles and lower the wave extension, that means angular potential.
In this case,
No, not in this case.
well, we considered together with Francesca this case. I didn't present it. Yes, the nice thing is that when you introduce three atomic potentials, then you can have naturally higher order gradients. In the case of a linear chain, it is easy to determine what is the analytical form of these higher order gradients. In the case of three-dimensional system, it is really very difficult because especially when you have the long-range interaction, the kind of possible terms that you can take into account to write the equation of motion is really dramatically high. So it takes a lot of time. There is not any kind of conceptual difficulty, but there is a technical difficulty, and so we started to work on the first part. So at least now on the first part, we started to work together with Francesco 2 months ago. So we are trying to develop this kind of combinations.
So in one of your rules, you have introduced negative stiffness of springs because of, for instance, Coulomb force. Does it introduce some instability?
Yes, they can. So you must be, you have to carefully consider this point if you want to rely on practical system. Yes.
But there is a stable regime?
Yeah, there are. There are. At least, I would like to say this. In the case in which you have alternate sign along the chain, you have not any kind of instability. Looking at the continuous form, because this is indeed the beta coefficient was selected to be positive. But the stability considerations are developed for the continuous case. I'm not sure that if the continuous counterpart is stable, it is something that I can ask to you. It means that at the granular level, so before to perform the limit for delta going to zero, the stability properties are maintained. It seems to be resonant, but I'm not sure.
Because this was trying to gradient equation. Okay, good.
Can you, do you think that it's possible with this system of resonator to develop a system that is not downwind but
Increasing the yes, yeah. The reason is that you can shape, for example, the damping coefficient. You can shape the damping coefficient. You can shape this like that, or it's like that, but nothing conceptually. You can even have something that is a negative contribution, provided that some global energy conservation holds. That means you can have that in a certain time window. You have a spike of energy, but then this is what we call no-logarithm. So it's say that you can have this for a time window in which you have this, but in another time window you cannot maintain the same frequency dependence.
Alright. Another question. In this case, the range of the frequency of the oscillator is close to the.
Otherwise, so you can have that if this is the frequency band that you are considering, in order to have an effective interaction, you have that the frequencies of the system must be located at least some of them inside this band. Otherwise, there is not impedance match. They oscillate substantially independently.
No question. So thank you again.